Okay, so in this video we're going to look at angular momentum, and if you go into the formula sheet, you'll see that we have this set of equations over here, all the ones with an H, right? All of those are equations for angular momentum, and the H is basically your angular momentum, and then Ri is the position vector from a fixed point. So let's say that we had a fixed point O, and this was our origin. So we have x, y, and we have something like this, right? And let's say this thing is rotating, and it's also translating with the velocity vg, right? So Ri, remember I meaning that we're dealing with each and every particle, so Ri is just going to be the position vector from the origin or from a fixed point to a particular particle. So we can call that R1, and then this would be R2, and so on and so forth. Okay. And then M is just the mass of each and every particle, and then Vi is the absolute velocity of a particular particle. So just like we found the absolute velocity for the linear momentum of a particle, we can do the same for angular momentum. Okay, and for a fixed point, HO, this can be simplified into RG crossed with M total times Vg. Okay, so the angular momentum of a particle around a fixed point basically tells you how the entire system, it tells you the angular momentum of the entire system around that same point, right? And then if you're taking the angular momentum about the center of mass of the particle, or the system rather, then you're going to have everything is going to be relative to that, right? It's going to be relative to G, right? So in this case, back to this example over here, if you wanted to take the angular momentum about G, which is the center over here, we're going to say it's rho I, which is the relative position between the particle and the center of mass. So rho I is the distance from the center of mass to the particle. It's this vector over here. This would be rho I. And then Ri dot is again the absolute velocity, the absolute velocity of a particular particle, right? So if you have the absolute velocity of the particle and you can find its relative distance to G, which you should be able to do if they're asking you to calculate this, then you use this equation. If they're asking you to calculate, if they give you the relative velocity to G, or let's say they just give you omega, right, then you can calculate the relative velocity to G, and you're going to use this equation over here. Okay, so it's dependent on what they give you. Notice how both of them contain rho I. They don't have Ri, right? So remember, Ri is the distance from a fixed point to G. Rho I is the distance from G to a particular point. When finding Hg, we always take everything relative to G. The only exception is the velocity. You can either take the absolute, or you can take the relative velocity to G. It'll still give you the same answer. Okay, and then if you're taking it about an arbitrary point P, right, and let's say that P was moving, for example, then we'd need to take RG relative to P, right? So the distance of the center of mass relative to a point P, right? And then cross that with M Vg plus H of G, right? So I'll explain this one, I'll break this one up a bit more, but let's first try and understand exactly what the angular momentum is, right? So angular momentum is the moment of momentum, right? So if we have a object that is just going through fixed axis rotation like this, right? So you have particle 1, 2, 3, and 4, and they're all rotating about a center. Let's call that center O. Okay, this thing isn't going to have linear momentum, right? Each and every particle will have its own linear momentum, right? So remember, linear momentum is literally just the mass times the velocity, okay? But the total momentum, so if you wanted G of the system, then we would take the sum of the linear momentums, or we could say that it's equal to M total times Vg, right? Cool. Since I'm going to call this point G, this point over here, I'm going to call that G. Since point G doesn't have a velocity, the system isn't translating, right? So can we say that this thing doesn't have momentum? So the linear momentum will be 0, but momentum is basically the mass times the velocity, right? And this thing is spinning, so shouldn't it have some sort of momentum? And it does. It has angular momentum. So it doesn't have momentum in terms of it translating, moving left, moving right or left or up or down, right? It doesn't have momentum like that, but since it's rotating, it has some sort of momentum associated with it rotating. That rotational momentum, quote unquote rotational momentum, we call that angular momentum. So just like we call this angular velocity, which is the velocity associated with something rotating, we define angular momentum as the momentum of something rotating, right? So yeah, cool. So how do we get this angular momentum? So angular momentum can be thought of as like the moment of momentum. So you'll see with this equation over here, the equation for HO, which is the sum of Ri. So Ri is your vector crossed with MI/Vi. So this MI/Vi, if you remember, this is just equal to G. So remember we said G is equal to the sum of MI/Vi. Okay, cool. So this is literally the same as saying the sum of Ri crossed with G. Okay, so if you think about it, this is kind of similar to the moment equation, which is the sum of moments equation, which is the sum of individual unit vectors crossed with the individual forces, right? Or put simply, if you have one force, right, you take its unit vector, so R crossed with its own force. So in this case, we're treating G kind of like a force. It's not actually a force, right? But we're treating it kind of like that, right? And if we do that, we can define angular momentum, right? So yeah, I hope that kind of makes sense. So that's what I mean by the moment of momentum. We're literally just taking the momentum and crossing it with a unit vector. And yeah, you can kind of think of it as the momentum will cause a moment about a specific point. Yeah, hope that kind of makes sense. So if this thing is rotating in this direction, then you'd have V2 going in that direction, V3 going in that direction, V4 in that direction, and V1 in this direction. And then to get the angular momentum about point G, we're going to say that it's equal to the sum of Ri crossed with Mi Vi, right? And then we're going to say that Hg is equal to, let's say that all of these distances were R. It's going to be R crossed with M1 V1 plus R crossed with M2 V2 plus R, and all of these are vectors. R crossed with M3 V3 plus R crossed with M4 V4. Okay, so we basically take, when it's relative to G, we take the sum of all the particles, the sum of the angular momentums of each and every particle relative to G, right? And you can see that this Ri is the distance from G to the specific particle, so it's a relative distance. If I defined my axis system here, or let's say this was O, which is a fixed point, then yeah, you can see that I'm taking it relative to G and not relative to this point O. Cool. Hope that kind of makes sense. And then what if G is moving now? So let's say that we had, I'm just going to simplify it. So we're going to have two balls on either end and then one in the middle. And then we have a velocity Vg, but this thing is also rotating. And then you have particle 1 and particle 2. So if we were to take everything about G, so we wanted to find the angular momentum about point G, we're basically taking the moment of momentum about point G. Yeah, hopefully that makes sense. And remember, we can use either one of these equations. So we could use this one, which has the absolute velocity, or we can use this one, which has the relative velocity. Okay, so what does that look like applied to this question? Let's do it first with the absolute velocity. So we're going to write our equation, which is rho I crossed with mi vi, right? Then rho I is basically the distance relative to G. So for particle 1, it's going to be this vector over here. For particle 2, it's going to be that vector over there. So you just find those respective position vectors. And then for Vi, so let's find V1. We can take V1 relative to point G, right? So this is point G. And we can say that V1 is equal to Vg plus V1 relative to G. Okay, and then it's going to be equal to Vg plus omega crossed with R. Right, and this R is again this position vector over here, right? So it's essentially the same as saying it's Vg plus omega crossed with rho I, right? And yeah, all of these are vectors. So cool. That's for V1. For V2, we do the same thing. We say V2 is equal to Vg plus V2 relative to G, right? And that's going to be equal to Vg plus omega crossed with rho I, right? And that rho I is just, again, this vector here. So you can call this rho I too, if you wanted to make that distinction between the two of them. Okay. Cool. Then, hopefully you can see that each particle is going to have a velocity caused by its rotation around point G. So this thing is rotating and it's translating. So each point or each particle is going to have a velocity due to rotation, right? And a velocity due to translation. So the velocity at point 1 is not just going to be omega times r. To this omega times r, we need to add to it whatever Vg is, right? So yeah, hopefully you can see that. And that's why the absolute velocity becomes this entire equation, right? And not just Vg. Okay, then we can substitute everything back into this equation and we can solve for Hg. If we wanted to use the other equation, the relative equation, all we need to do is find the velocity of each particle relative to G, right? So for particle 1, we need V1 relative to G. And we know that from chapter 5, we can break this down into omega crossed with R, right? As we did here and here. So this will just simplify to omega crossed with rho 1. Okay. And then same with particle 2. We need the relative velocity of particle 2 with G, which is just V2 relative to G. From chapter 5, we decompose this to omega crossed with R, which is going to be equal to omega crossed with rho 2. Okay, and that's it. So depending on which one is easier, you would either use this one or you would use this equation. Okay, but what if we had the same situation and we wanted the angular momentum about a fixed point, right? So let's call this fixed point O. So this point isn't moving, right? That's very important. You'll see as we get to point P, we're going to define point P as a point that can actually move, right? If this point is not moving and we wanted the angular momentum about it, we can, it's up to us if we want to take the angular momentum of each and every particle about point O. So if you look at the equation, you can see that we are summing the angular momentum of each and every particle about point O, right? Or we could simply simplify that to HO is equal to RG crossed with M total times Vg, right? So remember that, okay, just gonna erase this. Remember that this over here gives you the momentum, right? And we discussed in the previous video that the momentum can be broken down into the sum of the momentums of each and every particle, which is what this equation gives us. Or we could say it's the momentum of the entire system. So if we're considering the momentum of the entire system, we use Vg, right? And if you remember back to FSK, whenever we had like something that we wanted to take the momentum of, right, we wouldn't consider each and every each and every like component of that specific object. We just treat it as like a singular point, right? That us treating it as a singular point is us basically looking at how the center of mass of that object moves, right? So if this box had a velocity vg, and if this box had, let's say, marbles inside of it, let's say it had a velocity v, and we wanted to track its movement, what we could do is we could look at the velocity of each and every individual marble, or we could look at the velocity of the entire system. The velocity of this entire system would be the velocity of its center of mass, right? So yeah, hopefully that makes sense. So this gives us an easier route to calculate HO. So we could either do the sum of each and every particle, which would take time, or we could just look at the velocity of the center of mass and use the total mass to calculate that. And then the R that we would use in this case, if we'd use the center of mass, would be RG, which is the unit vector to the center of mass. So this would be your RG. Okay, which is just the unit vector from the fixed point to the center of mass, and then you cross that with Vg. Sorry, M total times Vg, and then that will give you HO. So obviously to use this equation, we would then need to know the position to the center of mass. So yeah, it's up to you. You might be given the position to each and every particle, which might be faster to use. So you could use this formula in the formula sheet, or you could, if you have the position to the center of mass, then it's a lot easier to use this equation. So yeah, just tread carefully when deciding which one to use. Yeah, then let's say we have a arbitrary point P, and let's say that P has its own velocity, right? So I'm going to draw the same system as before, right? Okay, and then it's rotating and it's also translating. And then let's say we have a particle P, and P has its own velocity. Okay, in the formula sheet we have this part over here, right? So this M times Vg, that is the momentum of the entire system, right? And this Rg relative to P is the is the position vector from P to G, right? So just as we did with point O, that basically describes P not moving, so we're treating it as kind of like a fixed point, right? And we're taking the angular momentum about point P, right? So this accounts for the object going through pure translation, right? So it doesn't account for it actually rotating around point P or moving relative to point P, right? So this part over here just describes it translating. Okay, so in this example over here, we're going to divide it into two parts. So we have this part over here. Okay, let me not actually say that P is moving. Okay, yeah, let me not actually say that. Let's assume that P is stationary. I can't really remember if P has to be a fixed point or a stationary point, but it should be in the supplementary notes. Yeah, so cool, just a disclaimer. Yeah, let's just treat it as a stationary point to be safe. But we're going to divide it into two sort of scenarios. So this thing will be translating, and it's also going to be rotating, right? And in each scenario we want the angular momentum about point P, right? So for the first part over here, our angular momentum about point P is going to be given by this portion over here, right, which is just R G relative to P crossed with M phi G, which is the same as what we had in this case over here, right? So we're going to have R G relative to P, and that R G relative to P is basically this vector over here. So R G relative to P crossed with M total times phi G. Okay, and then for the rotational component, we want to describe how everything is rotating, right? So it's only rotating about point G. So the only angular momentum caused by rotation would be the angular momentum of each particle around point G. So we'd need to find Hg, which would then be equal to, if you go to your formula sheet, we could use either this equation or that one, right? So it's going to be rho I, the sum of rho I crossed with mi. I'm going to use relative, so I'm going to use mi rho I dot. Okay, so it's going to be, if I define this to be R, it's going to be R, let's call that R1, crossed with M1 rho 1 dot plus R2 crossed with M2 rho 2 dot. Okay, and then you add both of these components together to get the total angular momentum about point P. Okay, hopefully that makes sense. Yeah, And then for this question, they ask us to determine the angular momentum about body G and about point O. So when determining it about G, we use this equation over here. So we can either use the absolute velocity or we could use the relative. So in this case, I would probably use the relative just because it's a bit quicker. So we're given the angular velocity. So our relative would just be omega crossed with r. Okay, so I'm going to start with hg, and we know that hg is equal to the sum of rho I crossed with mi rho I dot, okay, which is equal to, it's going to be 2 times, because 2 of them have the same distance, right? So you can like do it for each and every one. It's still going to give you the same answer. So it's going to be 2 times. Let's call this position vector R1. It's going to be R1 crossed with, and we're told that each thingy has a mass of 0.5, crossed with 0.5 into omega crossed with R1, okay, plus 2 times R2, which is going to be this one over here, crossed with 0.5 into omega crossed with R2. Okay, and for R you could use either one of these vectors. It's either you use that one for R2 or you could use this for R2. Okay, it's up to you. Yeah, and then for HO, we just going to use this equation over here, but instead of using the sum of the angular momentum of each and every particle, we can use the angular momentum of the system, right, of the entire system, which would be HO equal to RG crossed with M total times Vg. Right, and yeah, you'd be able to get, since you have all of these dimensions, you'd be able to get Rg. So using this wouldn't be an issue. Okay, hopefully that makes sense. And then in this question over here, we're told that we have 3 small spheres that are welded to a light rigid frame which is rotating in a horizontal plane about a vertical axis through point O with an angular velocity of 20 radians per second. If a couple moment MO equal to 13 Newton meters is applied to the frame for 5 seconds, we're asked to compute the new angular velocity using that info. So you can see that for this question we've given a time of 5 seconds and we have a moment. Okay, so our angular velocity that we defined or that we were calculating previously was just for a singular point in time. So just like linear momentum, right, we can write an integral for the momentum. So if we were looking at the angular momentum about point O, which we are in this case, then the integral from t1 to t2 of HO dt is equal to the integral from t1 to t2 of the sum of moments about that exact same point. So these 2 points have to match each other. And then we integrate with respect to time. Okay. Now, in this scenario, we have a couple moments of 30 applied to the frame, right? And we're not told that it changes with time, so we can assume that it's constant, right? So this integral will simplify to the integral from t1 to t2 of 30 dt, right? And since 30 is a constant, I'm just going to simplify this to delta HO. So a change in in angular momentum will become 30t evaluated from t1 to t2, right? So this is what our integral will simplify to, and this will be equal to 30 t2 minus 30 t1. We can simplify this to 30 t2 minus t1, which is equal to 30 delta t, right? So rewriting this, we can say that delta HO is equal to 30 delta t. Okay. And remember, if we wanted our angular momentum to be conserved, then we'd need to look at a specific point where the sum of moments are 0. So let's say that we had a rod that was swinging like this, right? So it was swinging, it's going through fixed axis rotation about this hinge over here, right? And let's say that this hinge was frictionless, right? And let's say that this point over here was G, and this point over here was O. Okay, if this is frictionless, and they told you that it starts from this angle, let's call that theta. So this angle is theta, that's state 1, and it moves to state 2 over here, right? And let's call that theta 2, right? And they asked you to, calculate something regarding this, maybe like the velocity at point 2 or something like that. Or like if they asked you to calculate, the velocity. Let's say they asked you to calculate the velocity at point 2. So in this example, if you were to draw the free body diagram for this thing, you have a force going up, a force going there, right? And you have mg, right? So because you have all of these forces, right, you can't say that linear momentum is conserved. So you wouldn't be able to use linear momentum to solve the problem, right? So you'd need to resort to angular momentum, right? And you'd need to then pick a point where the sum of moments would be 0 in this scenario. So since the joint over here has been said to be frictionless, we'll take sum of moments at this point because we know it would be 0. There's no resistance to its motion, so you won't create a resistive moment. So the moments there would be 0. So you would get that H at O, in this case over here, would be equal to T1, T2, sum of moments at point O, but this would be equal to 0 because sum of moments at O is equal to 0, right? And then, yeah, you would be able to solve using that. Yeah, hope that explanation makes sense. So that's how you'd use conservation of angular momentum, but in this case it's not conserved because there is a moment applied to it, but we're also told the time interval it's applied for. So if you look over here, we're told that it's applied for 5 seconds. So we know that delta HO would be equal to 30 times delta T, which is going to be 30 times 5, which is the 5 seconds it was applied for. Then this will equal to 150. And then at state 1, we're given the angular velocity. Okay, and we're asked to calculate the angular velocity for state 2. So to get HO, HO1 would be equal to the sum of Ri crossed with Mi Vi, right? Okay, and because it's going through fixed axis rotation about point O, this is just going to be R1, for example, plus crossed with, M1 into omega crossed with R1, right? So if you were to do relative velocity V1 equal to VO plus V1 relative to O, then VO is 0 because it's a fixed point, and then this would simplify to omega crossed with R1. So that's where this comes from. Okay, if point O had its own velocity, then you wouldn't remove that. So yeah, but because VO is 0, then it simplifies to just omega crossed with R1. Okay, then you do this for each and every point, and you'd be able to find HO, right? So we have all the values for this case. Problem is with HO2, we don't have the angular velocity at state 2. So it's the same exact equation. We're going to say we have we're going to have the sum of Ri crossed with Mi Vi, but let's just call it 2 for state 2. Okay, then this will give you R1 crossed with M1 into omega 2 crossed with R1, right? And this is the thing that we're trying to solve for. So you do this for each and every particle, right? Okay, you won't be able to solve for it, but you know that HO2 minus HO1 is equal to 150. So this delta H, we simplified it to HO2 minus HO1, right? Which is what we put over here, and that's equal to 150. So you write the answer from this equation, and then substitute that there, and you'll be able to solve for omega 2. Okay, hope that makes sense.